Associative property of vector addition. Welcome, everyone. Today, we are going to delve into a fundamental concept in vector algebra, the associative property of vector addition. Now, before we dive into the new material, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on how to combine two vectors using the triangle law and the parallelogram law. Those methods were excellent for understanding the interaction between a pair of vectors. However, in the real world, whether you are calculating the total displacement of a moving object or analyzing complex forces in physics, you will often encounter situations involving 3, 4, or even more vectors acting simultaneously. This is where the associative property becomes essential. It provides us with the mathematical framework to group and add multiple vectors efficiently, and over the next few slides, I will show you exactly how this property works and why it is so powerful. Understanding the associative property. Now that we've recalled how to add two vectors using the triangle and parallelogram laws, let's look at what happens when we have more than just two vectors to deal with. This brings us to the associative property. Essentially, this property tells us that when we are adding three or more vectors together, the way we group them using parentheses does not change the final resultant vector. To put this into a mathematical language you can use in your calculations, we express it as a vector A plus vector B, all enclosed in parentheses, plus vector C, is equal to vector A plus, the quantity vector B plus vector C, all enclosed in parentheses. This holds true for any vectors A, B, and C. The real beauty of this property is the simplification it offers. Because the grouping doesn't affect the outcome, we don't need to get bogged down in complex brackets. We can simply write the sum as vector A plus vector B plus vector C. This makes handling long sequences of vectors much more manageable, which we are going to see demonstrated geometrically in the next few slides. Geometric demonstration. Now that we understand the mathematical definition of the associative property, let's move from the abstract formula to a visual geometric demonstration. To do this, I want you to imagine a series of connected arrows or sequential segments stretching through space. We will label the endpoints of these segments with the points P, Q, R, and S. To make our proof precise, let's define our three vectors clearly. First, we have vector A, which represents the directed segment from point P to point Q. Next, we have vector B, which starts where the previous one ended, moving from point Q to point R. Finally, we have vector C, which moves from point R to point N. Point S. By setting them up this way, we are creating a continuous path, which will allow us to test both ways of grouping these vectors in the next few slides. Evaluating \vec A plus \vec B plus \vec C $. First, we are going to group vector A and vector B together, applying the triangle law we learned previously. When we add vector A, which is the segment from P to Q, to vector B, which is the segment from Q to R, the intermediate point Q is essentially bypassed. This leaves us with a single resultant vector, which is the vector from P to R. Next, we take this new result and add our third vector, vector C, to it. In terms of our points, this means we are adding the vector from P to R to the vector from R to S. Finally, we apply the triangle law one more time. Since the end of our first group is point R, and the start of vector C is also point R, they connect perfectly. This brings us directly from our starting point P to our final destination, S. So, the total resultant for this specific grouping is the vector P to S. Now that we have defined our three vectors, let's walk through the first way to group them to see what happens. Evaluating \vec A plus \vec B plus \vec C $. First, let's focus on the part inside the parentheses. We are going to group vector B and vector C and apply the triangle law, just like we did in the previous slide. If we take vector B, which is the segment from point Q to R, and add vector C, which is the segment from R to S, the triangle law tells us that the resultant is the vector from the very start of the first vector to the end of the second. So vector b plus vector c equals the vector from Q to R plus the vector from R to S. which simplifies to the vector from Q to S. Next, we take our original vector and add this new resultant we just found to it. This gives us the expression vector A plus the quantity vector B plus vector C. Substituting our result from the first step, this becomes the vector from P to Q plus the vector from Q to S. Finally, we apply the triangle law one more time to this new pair. Since we are moving from P to Q and then immediately from Q to S, the combined path leads us directly from the starting point to the final destination. Therefore, the final resultant is the vector from P to S. Now, let's look at the second way we can group these vectors to see if we get the same result. On this slide, we are evaluating the expression where we group vector B and vector C together first. As you will see on the next slide, this result is exactly what we obtained in our first calculation, which brings us to our conclusion. Conclusion of geometric demonstration. So let's bring everything together. If you look back at what we just did in the previous two slides, you'll see that whether we group the first two vectors together first or group the last two vectors together first, we arrived at the exact same destination. In both cases, the final resultant vector is the vector from point P to point S. Therefore, we can mathematically conclude that the quantity vector A plus vector B, all in parentheses, plus vector C, is equal to vector A plus the quantity vector B plus vector C, all in parentheses, and both of these are equal to the vector P to S. This confirms that the grouping doesn't change our final result. Real-world example: navigation of a drone. Now that we have seen the geometric proof using points P, Q, R, and S, let's step away from the abstract diagrams and look at how this applies to a real-world scenario. Imagine a delivery drone performing a three-stage flight. In the first stage, the drone departs from the warehouse, which we'll call point P, and flies to a waypoint, point Q. We can represent this first leg of the journey as vector A. For the second stage, the drone moves from waypoint Q to another waypoint, point R, which is represented by vector B. Finally, in the third stage, it travels from waypoint R to the customer's house, point S, which is our vector C. As we move to the next slide, we will use this exact flight path to break down the total displacement using two different grouping methods. Breakdown of total displacement. Now, let's apply everything we've just learned to a practical scenario to see this property in action. On this slide, we are breaking down the total displacement of our drone's flight using two different mathematical approaches. First, let's look at method A, where we group the first two legs of the journey together. Imagine the drone completes its first leg, vector A, and its second leg, vector B. If we group these first, we are essentially calculating the net displacement from the warehouse to the second waypoint. Mathematically, vector A plus vector B equals the vector from point P to point R. Now, to find the total journey, we simply add the final leg, vector C, to this result. This gives us the vector from point P to point S. Next, let's try method B, which is the alternative grouping. This time, we'll group the last two legs of the flight first. We calculate the net displacement from the first waypoint, point Q, all the way to the customer's house, point S in notation. This is vector B plus vector C, which equals the vector from point Q to the vector from point Q to point S. To complete the full trip, we add the initial leg, vector A, to this result. Once again, we arrive at the vector from point P to point S. As you can see, regardless of whether we group the first two legs or the last two legs, the final destination, the total displacement, remains exactly the same. This perfectly demonstrates the associative property we've been discussing. Key takeaways. First, let's revisit the definition. The associative property essentially guarantees that when we are adding vectors, the way we group them using parentheses does not change our final resultant vector. Whether you group the first two or the last two, the destination remains the same. To put this into a mathematical formula, we express it as a vector A plus vector B, all enclosed in parentheses, plus vector c, is equal to vector a plus vector b plus vector c, all enclosed in parentheses. Because of this property, we gain a huge advantage in simplification. When we are dealing with a long chain of vectors, we don't need to worry about complex nesting or parentheses. We can simply write it as vector a plus vector b plus vector c, and so on, and just continue adding them one by one. Finally, let's look at the geometric meaning behind the algebra. When we perform sequential, or head-to-tail, addition, the final resultant vector is always the single vector that connects the very first starting point to the very last terminal point in the sequence. All right, let's bring everything together and recap the key takeaways from today's lesson. Now, before we wrap up, I want to point out a few common pitfalls to avoid in your upcoming practice problems. Common mistakes. First, be very careful not to confuse associativity with commutativity. I know they sound similar, but they refer to two different things. Remember, associativity, which is what we've focused on today, is all about grouping or where we place our parentheses. Commutativity, on the other hand, is about the order of the vectors, such as switching vector a plus vector b to vector b plus vector a. While it is true that both of these properties apply to vector addition, they are distinct concepts, so make sure you use the right terminology. Second, when you are performing a geometric proof like the one we saw with points P, Q, R, and S, always ensure you are using correct vector sequencing. You must place your vectors head to tail to accurately demonstrate the property. If the vectors aren't connected correctly, the geometric logic falls apart. Finally, a very important warning. Do not assume that this property applies to all mathematical operations. While we have proven that vector addition is associative, please note that vector subtraction is not. If you look at the expression, vector a minus vector b minus vector c, it is not equal to vector a minus the quantity vector b minus vector c. The grouping matters immensely when subtraction is involved. Now, as we wrap up our lesson, I want to highlight a few common pitfalls to watch out for so you can avoid making mistakes in your exams. Keep these points in mind, and you'll have a much stronger grasp of vector algebra. Great job today!